the reason why we are using this Laplace transformation is because they are very useful to solve simultaneous set of ordinary differential equation. Okay, so not one ordinary differential equation, but if you have like sets of ordinary differential equations simultaneously, meaning that dy1 by dt is 5y1 plus 5y2, and dy2 by dt is 5y1 minus 3y2, bunch of different ordinary differential equations together, it's a piece of cake to solve them using Laplace transformation. Alright? So let me start directly by 6, 7. That's the application. I'll show you a flavor of what we'll be able to accomplish by the end of the class. Alright? So you had a problem like this. It's a rate equation. Basically, two tanks. Initially, this tank didn't have any salt in it. 100 gallon of water. This tank has initially 150 pound of salt per 100 gallon of the tank. Okay? And then he starts basically flow coming in like this. And that flow eventually will leave here. So 6 gallon per minute coming in and they are leaving there. But also to keep this mixing between the two tanks, so that the concentration wouldn't increase in one compared to the other, there's also internal loop which basically take 2 out of here and send it there. So there is a 2 gallon per minute basically just keep recirculating on top of the 6 coming in and leaving. Okay, so as a result you can guess that the concentration here will dilute. Exactly, you eventually will get diluted, right? And that zero concentration, no salt whatsoever, it will build up. And so in this problem it's required to calculate the concentration as function of time for the two tanks. Alright? And so we will see how we can, it's fluid mechanics problem. It's basically we control volume and we'll write the continuity of conservation of mass of the salt. And we will come up with two differential equations. Okay, see dy1 by dt and dy2 by dt. y1 and y2, that's the concentration here that start with 0, and y2, that's the concentration here that start when the clock started, when the problem started counting, that was 150. Right? And you are supposed to solve those two ordinary differential equations. What's the meaning of ordinary differential equation? Ordinary differential equation as compared to partial differential equation. The equation is partial differential equation if what?
There's a different variable.
No, not the different variable. The t, the independent variable, the y1 is not function just of t. Y1 is function of, function of time and x, for example, or height. So not only you are solving the concentration in the tank per time, but also the concentration in the tank per time and height. That become partial differential equation. So y1 is function of height and time, and y2 is also function of height and time. This become partial differential equation. Those are horrible. Let's leave them for the end. But those are a little bit easier. This is ordinary differential equation. So y1 is only function of t, and y2 is only function of t. You can have 100 y. We could have this not just 1, 2 tank. It's a network of tanks connected. Big refinery, tons of tanks. You're bringing oil from the Gulf or something, and you're bringing them to the tank, and they are distributing the oil, and you want to basically figure out the height of each tank or something like this. So you could have different y, but all of them are just function of time. It's still ordinary differential equation. Right? So what will determine the ordinary or partial? It's this guy. Okay? And the fact they are simultaneous is because the equation for y1 has y2 in it, and the equation for y2 has y1 in it. Okay? Last year there was a problem like this in the midterm, and one student didn't notice they are y1 and y2. They thought that everything is just y1. Of course, like, why would I have minus 8y1 plus 2y1?
Nice easy equation to solve.
So he solved each one of them by itself. Of course, you don't even need Laplace. You don't need anything. You can just do separation of variable. Let's put y1 in one side, put the time on the other side, and integrate, right? No, because they are coupled like this. Here is the magic, the beauty of Laplace transformation. is that this solution, if I ask you right now to give me y1 of t, it's really hard to get, right? But the Laplace transformation take those function with their derivative and turn everything into the S domain. So the function will look different in the S domain, okay? Rather than things function of t, they will be function of S. Now, once they are y1 of S and y2 of S and everything of S, okay, and don't ask me what is that S. Once everything is function of S, it's very easy to get y1 of S and y2 of S. Of course, that solution in S domain doesn't mean anything with respect to the time. So we have to go back to with the inverse Laplace. So when I say this mark is basically kind of Latin for Laplace, L basically, and this is basically going back L minus 1, I'm taking the inverse Laplace. And so once we find the solution, which is very easy, we go back here and turn it into the actual function of time that we want. Alright? So that's why for the next 81 slide, we will have to learn how to do that step and how we go back to that step. Of course, right now we should guess that, you should know that there is no free lunch. Huh? How come it's like so easy to get the solution over here? Well, the price is this transformation. So the price is actually to turn f of t into f of s, whether this f of t is sine t or cosine t or just t square or t, the price is to do that integration. So that integration is that you bring this f of t, whatever that f of t is, you multiply it by, this is not e to minus 5t, this is e to minus st dt, and the integration from 0 to infinity. So you can guess that after you do that integration, which is on t, all the t will disappear because you're substituting by 0 and infinity. And so what will happen here is just function of s. Huh? So for example, sine omega t will end up being, some omegas and some s. So right now you should feel what? You should feel worried, because the problem with those guys that you didn't really want to integrate the ordinary differential equation, right? And you were looking for an easy solution, and that was sound like magic solution. Let's take the Laplace, solve it easily, and come back. But then it turned out that you still have to integrate to do that thing. But the good news is that those integration has been done. We have the table for them. And you don't even have to memorize. When I was undergrad, I had to memorize this transformation. But you have the tables at the end of the chapter. So basically, any function, you know the transformation, you know that integration, the result. So you will not really do the integration. All right. So the price is kind of bait forward. Someone already did the integration and figured out how to turn every function into that S domain. And so we will capitalize on this, use all those transformation to turn everything there, solve it, go back with the answers. However, the tables have some kind of the building blocks, but it's like that. If it's a car, for example, they have the transformation of the wheel, the transformation of the door, the transformation of the window. But then the problem will come as, well, here is a car, transfer it to the S domain. You actually have to look with your eye and figure, this is a car, I see a wheel, I see a door, and then you transfer each one. So it's not as easy as, here is a wheel, go transfer it. No, you have to spot those building blocks, you have to spot those functions. That will be the only difficulty that we will have. All right? So let's actually see how it's being done. So any f of t, okay, to do the Laplace of that f of t, that new function will be f of s. And to make our eye clear about this, basically it's the thing when it's function of time will make them small f, and when they go to the S domain we'll make them capital. All right? So this way you don't even have to write f of t and f of s. That's why you just He's simply just saying the Laplace of f. But if it's understood that if it's small, then that's in the t domain. And if it's capital, okay, then that's the s domain. Alright? And again, the integration in case you cannot see, it's 0 to infinity e to minus st f of t dt. Alright? The inverse is basically going to be L minus 1. And so simply, again, when it's capital like this, when it's cap, that means it's f of s. Right? S domain. I really think, you know, it's a magic concept, you know. Only engineer will appreciate this, you know, like you are turning the solution to some domain that you don't know what it is, but it's just very convenient mathematically. So let's deal with it and get the solution there and then come back. Not so many people will really get this concept. All right, so he's basically simply saying that the inverse of the Laplace will end up going back to the same function, right? And the same thing, Laplace of the inverse is basically just the inverse, right? So you go to the t domain and the s domain, and then when you go back again, you go to the t, and then you go back one more time, you go to the s.
So you use the exact same table, except once you're going back, you look in the f and t column and find something, and then your
right.
T
So
domain is back to
right, we'll see those tables, and so those tables work both ways basically. But let's see some of the transformation, and we'll answer this question one more time. Right. So let's start with a constant. If the function is the equation, look at the equation that we care about, that hopefully we'll solve at the end of the class. We had the 6, for example, and had y, and it could have sine and cosine and sine, and so let's start with a constant, just 6. How you transfer a 6 into the s domain? It becomes constant over s. How do I prove this? Well, do the integration here. He's basically trying to find the transformation of the Laplace transformation of 1, a constant 1. Okay, this is just to remind you before we do this integration, since we have e to the power minus st, it's important for you to remember this. So I would just recall that the integration of e to the power at is the same e to the power at, but we divide over whatever is here. You remember that? Huh? Very good. So again, by definition, if you want to get 1, you want to get the inverse, the Laplace of 1, you basically say I would put 1 here. There's 1 here multiplied by e to minus st. We just don't see it, but there's 1 here. So e to my power minus st multiplied by 1 dt. And we are integrating e to the power minus st, similar to e to the power at. E to the power anything is e to the power that thing, e to the power minus st, divided by 1 over the number multiplied by the t. Okay, so what is the number multiplied by the t? It's minus s. So it's 1 over minus s. 1 over minus s. And what are the limits? 0 to infinity. Okay, so you substitute at and 0, you will get 1. You substitute at infinity. That's what I'm doing over here. So between 0 and infinity, you get basically 1 and you get 0. Right? So it will end up being basically minus 1 over s and multiplied by 1, and 1 over s multiplied by 0. So, and there is minus over here. So anyway, you get 1 over s. So this is the last time you're going to do this integration. Right? It's basically, now anytime you see 1, it's 1 over s. 5, of course, because the 5 will just basically be outside. Doesn't really go into the integration. Right? So basically any c will end up being c over s. Good. Now, if the function is e to the power at, the Laplace is 1 s minus a. Okay. For example, if it's like e to the power 5t, it's in that form, e to the power something t. The Laplace is 1 over s minus 5. Okay. How do you prove this? You just put it inside the integration, hit it with e minus st, and you integrate from 0 to infinity. When you have two guys, e to the power ax multiplied by e to the power bx, it's basically e to the power a plus b. Ax plus bx. So basically, let's add them together. It's basically the integration of e to the power minus s plus at. And so the same integration we did before. It doesn't matter what's next to the t, you just divide over it. Right? So that's a minus s, and that's the same thing, and you substitute from 0 to infinity, you'll end up getting s minus a. Alright? Very good. So because it's integration, the Laplace is integration. If you want to integrate this function, a plus a f of t plus b g of t, if you want to integrate this function, what do you do for integration? You split them, right? You split the integration on them. So it also, we will split the Laplace on them. So that's very nice that it's linear. That basically means that an equation like this, all we have to learn is basically what's the inverse, what's the plus of this by itself, what's the plus of this, what's the plus of this, what's the plus of dy by dt. And so the Laplace of that equation, left hand side, right hand side, it's basically the Laplace of each one plus the other one, right? So each one by itself. You got it? So that's what makes it very easy to use. So the Laplace is linear because it's integration. The cosine and the sine, and our homework has a sine this week in it. What is the cosine and sine? You guys remember? Right. It's the hyperbolic cosine and hyperbolic sine. And so the Laplace of the cosine is s over s squared minus s squared. And the Laplace of the sine is a over s squared minus a squared. Okay? And he's trying to prove it. And this equation is going to be very useful for your homework too. The cosine at is half e to the power at plus e to minus at. And for the sine, do you remember what was the sine? The cosine is half this plus this, and the sine is, it's here. It's half e to the power at minus e to minus at. So one of them is plus and the other one is minus. Okay? So anyway, whatever, whether it's cosine or sine, and you would like to get the Laplace, what do? You basically, because later for the table, but we are trying to figure out how did they come up in case there is something new. In case there is something that's not in the table. This is how you do it. So he's basically saying, well, let's split this into its original definition, which e to the power at and e to the power minus at. And then the Laplace will divide itself into the two of them. Because we are integrating, so we can integrate the first one and then add the integration of the second one. So it's Laplace of this plus the Laplace of that. And so e to the power at, that's s minus a. And e to minus at, that's s plus a. And then it's very easy to basically just multiply this by this. S squared minus s squared, right? Remember, s squared minus s squared is, this is also very useful relation for us. S squared minus a squared is s minus a times s plus a. Of course. Okay? And so, he just proved that for the cosine it's s over s squared minus a squared, and you can see here that for the sine it's the a over s squared minus a squared. Got it? Question about this? So Sean is right that actually, if you would like to, in the homework, or the quiz next week, if you get what is the cosine, you can go ahead and use the table. You don't have to do this. You basically open the table and figure out what is the Laplace for the cosine, and it will tell you it's s over s squared minus a squared. Okay? But if the quiz or the homework basically have what is the Laplace of cosine at plus sine at, then you split the Laplace on the two of them. You say it's Laplace of this plus the Laplace of that. And then you go after each part and basically come up with its Laplace transformation. Questions so far? Piece of cake. We have 40 more pages like this. Okay. No, less than that. Cosine, cosine omega t or at or what, that's a constant, okay? So that omega is basically a constant. You don't have to worry about it. So let's look at the homework for a second. Homework 5. So see, he said, what is the Laplace of cosine square omega t? So omega is constant. He say omega is constant. So it's like 5, 7, 8. Don't worry about it. It's the cosine square omega t. So unfortunately, the table doesn't have cosine square. So we have to use that concept that we have to break this into things that we know that exist in the table. Okay, we want to break it into things that actually exist in the table, so that we can use the table on them. All right. Very good. So the cosine by itself, without the square, you get s over s squared. That's very similar to the, look at this, it's very similar to the cosine, except
It's addition instead of subtraction.
exactly, except for the minus, it's the plus. So this is very useful when you actually you end up with something like this, and you would like to go take the inverse Laplace. You want to go here. You got the solution in S domain, and it's s over s squared plus omega squared. The inverse would be the cosine, but if it was s over s squared minus omega squared, it end up being cosine, not cosine. So the minus is a big deal. Okay, and the same thing for the sine, omega over s squared plus omega squared, but here it was omega over s squared minus a squared, or omega squared. You got it? Well, what if I would like to get the inverse of 1 plus s squared plus 4? If only I had 2. What should I do? Excellent. Multiply by 2 and divide by 2, and this would be the, here is the cosine, sine, and then the half basically come next to it. Alright. So here is the proof for the cosine. I will save you the agony, because he's basically doing it by parts. Because you see, remember when you're integrating e to minus st multiplied by cosine omega t, how do you do that integration? So integration is not as easy as differentiation, right? Anything can be differentiated, but for the integration sometimes it's hard to actually do this part. So this, I'm trying to remind you of the integration by parts. Okay, if you are integrating something like this, f dg, or basically it's kind of like f g prime dg. So you basically, or dx or dt, then you can this is dt. Then you can basically pull those two guys together, and you would think, well, that's simply dg. Or basically I can integrate this one, okay, and then differentiate the second one. Alright, and the limits a and b apply to all of them. You remember that part? That was my favorite when I was a freshman. That's my freshman math course basically. So what you do over here is basically you would look at this and you would say this is actually, this guy is gonna be the one that I'm gonna integrate. Okay, so that's the G and that's the F. Right? So E minus ST you integrate it over here from 0 to infinity, and then you differentiate the cosine. And so of course the differential of cosine is minus omega sine omega t. So the cosine become minus omega sine omega t dt. Right? So, and so this is basically, you substitute the two limits over here. Okay, so those two guys will end up being 1 over s, and we have e to minus st sine omega t. That's like the same problem again. I mean, we were started with e minus st cosine, we end up with e minus st sine. You know where things are going? How's that gonna finish? Do it one more time. The sine will disappear and you will end up being cosine, which is the original one. And so you will get the integration showing up twice with bunch of stuff. You pull it on one side, and here you have the integration. Right? So it's a very nice trick. So here he basically look at this integration and he decide, well, I'm going to integrate this and differentiate this. Integrate this, integration of e to the power at, it's the same over s, and he differentiate this and he end up with a cosine. So basically this, that's the integration he started with. Or basically let's call it I. See, all this time I'm calling this integration I. So now we end up having I equal bunch of stuff time I. So let's bring I together, and basically I is s over s squared plus omega squared. Does this make sense? Will I ever ask you to do this integration?
I hope
No,
not.
the focus is actually the Laplace, not really the integration. So I would like you to just remember this. Where did it come from? But appreciate the table. When you look to those table, I would like you to think that someone really did a very good job getting that table done. Okay. Each one of those integration is really a very long story. Right? So we have table for all those integration. Right? So table 6.1 for example. So someone did the 1, get 1 over s, the t, get 1 over s squared. Again, if you don't believe this table, basically just plug the t, multiply by e to minus st, integrate, you will get 1 over s squared. T squared, see it's kind of the t become 1 over s. So the multiplication become kind of division. You will see that seam working all the time. Things basically get upside down over there. Okay, so the t squared become 1 over s cube, and then you have a factorial 2, which is, what's the factorial of 2? 2 times 1. Let's call it 2 times 1, which is 2, right? And then so in general t to power n, where n is 0, 1, 5, 10, 100, it's basically factorial n over Sn plus 1. So t to power 7, factorial 7 over s to power 8. Piece of cake, right? And now t to power a, where a is positive, doesn't have to be integer. It become this thing. This is gamma function. Right? So also when I was being taught math, they taught us the gamma function without really telling us why this is important. That was really torture. So to take like a bunch of lecture on the gamma function without understanding why this thing is even important for you, that was like really, really torture. Alright? Especially if you are really trying to do a good job learning what is this gamma function. So the gamma a plus, the t to power a is basically gamma a plus 1 over s8 plus 1. So what is, before we finish that table, what is the gamma function? It's, so when you put this t to power a multiplied by e to power st, it will pretty much look something like this, right? E to power minus st times t to power, So this integration will show up in many other endeavors, and so someone basically decided to actually do this integration, and it ended up being, it actually show up like this. So this is the plot of the gamma function. Okay, this is figure 553 in our textbook. So the gamma function will look like this, and there are actually it's the value of that integration. And why do we need it in Laplace? Basically, if we end up getting any input function coming to our system, you know, you have a car and the vibration or a force or something, and it's t to power something. Okay, and you want to get the Laplace of something like this, you will have to use the gamma function of a plus 1. So how there are tables for it, but basically for integers, gamma k plus 1 is basically the factorial of k, right? So you'll find those gamma function in our appendix, and there are tables that explain them for us. But basically that's their definition, and that's the recurrence relation, or basically how you bring gamma of something plus 1 from its lower value, right? Very good. So back to the table. E to power at, we did this 1 over s minus a. You got cosine, sine, cosine, sine. Okay. Now this one, e to power at cosine omega t. We will actually explain this in a second, and this is important for this. See, it's e to minus t multiplied by sine 4t. So when you have e to power something multiplied by a function, how do you handle that? Ouch. For e to power at cosine omega t, that's this one, and e to power at sine, it's this one. For e to power at multiplied by anything, there is a rule for that, and we'll see it right now. Okay, but anyway, let's say that again.
It'd be nice if the ones you have there were in here as well.
That table is not in front of you?
They're there.
Huh?
No, that's,
Some of them are.
That's on 207. That table right there is on 207.
There are more tables at the end.
Yeah.
I'll show you at the end. There are a lot of tables. Don't worry. All right. So
207.
So guys, let's just see in general, if you have e to power at, e to power at multiplied by any function, sine, cosine, sine, cosine, like the homework, t squared, t over whatever. So the rule, it's actually very easy. It's called the first shifting theorem, and it's basically the e to power at end up shifting the s by s minus a. So basically what he's saying is that forget about e to power at. You have f of t, sine t. What is the Laplace if it's sine t? It was s over s squared plus 1, right? Sine t. And then you go after every s and you turn the s into s minus a. Right? Every s become s minus a. Right? And so that works the other way too. So if we are doing the inverse Laplace and we look to a function and it look almost like a sine, except that all the s's are s minus a. Every s is s minus a, s minus 5, s minus 5. Then it must have been not just simply sine, must have been e to power at multiplied by that sign. Alright? So here is example. So the cosine is s over s squared plus omega squared. And if you see s minus a over s minus a squared plus omega squared, see all the s are s minus a, including the square. Then you tell yourself this must have been almost cosine, but it has e to power at next to it. Right? And for example, if you see omega s minus a plus omega squared, that's almost sine, except the s is s minus a. So it's sine multiplied by e to power at. Okay, so that's the first shift property. Good? So here is an example. please find the inverse of something like this. So if you're looking to something like this, you know, you should basically try very hard to get the things in the form of s over s plus omega square or minus omega square. It doesn't matter whether you're going to go sine and cosine or sine cosine, but you want to have s over s square plus omega square, right? So the fact that we have s square plus 2s plus number doesn't look nice to us. Our table have basically the form that we are trying to look in our table should be something like this: s square omega square, plus or minus, it's okay, but we need this square plus this square. Of course, the omega square, it doesn't matter, you know, if it's 401, perfect. 401 is the square of the square root of 401. So this is the square root of 401 square, right? So don't worry about the number. This is basically the square root of 401 square.
Do s plus 1 squared plus 20 squared.
So we need, right, so Jason is right. He's basically saying, so if you would like to turn this into something square, you need to basically complete the second order. You need s squared plus 2s plus you need to turn it into s squared plus 2s plus 1, because this is s plus 1 squared. Is that clear? So how we can get the 1? Well, we have 401. We bring 1 from them. And even if we had 0, we add 1 and subtract 1. Right? So anyway, we bring the 1 over here. Now we had the square plus the square. Now we go upstairs in the numerator over here. And well, I wish we had s plus 1 too, so that we have, you know, the s plus 1 over s plus 1. So you look over here and basically you try to cook s plus 1 out of this thing. Okay? So 3s minus 137, how can I get s plus 1 out of it? 3s plus 3, so that I can take the 3 and then it becomes s plus 1. And whatever is left from the number, they stand by themselves. So now look at this. S plus over s square plus omega square. Right? So it's cosine. And then what happened to the s plus 1? That's e to minus t. That's the shift. Alright? And the 3, that's a constant. The 3 actually go outside immediately. We don't care about it. Constant always will come out. Right? And what happened to this 140? We actually need, since we have 400 here, we can only have omega. If this is omega square, then we should have omega here. So square root of 400. You divide over square root of 400, and which is 20, and then you have 140 over here. So 20 with 4, you get 7. And again, looking to this, it's s square plus omega square, and here there's omega. So that's a sign, but the s plus 1, that's the shift. So this is basically going to be your life in this chapter, that you have those tables, and those tables are basically, you have the standard form. Okay? The standard form are pretty much those guys. And so you will try to remodel. That's what I meant when I said the car. You try to look for the wheels and the door, and so that, because you know the transformation of the car parts, the wheel by itself, the door by itself, the window by itself. So you know the transformation of this by itself, by this, by this. So you have to look at the function, and you try to basically split it into the part that you have the table for it. Questions? Why don't we take a break? Did we take a break already? No, we didn't. It's so much fun. It's hard to stop.